Hello again. In our previous lecture, we have gone through the force control applications and we have learned how to control the interaction force with an environment when there is no loss. That is to say, when the environment model was only consisted of a pure spring model. In the second lecture of this series, I will make an addition on the previously made derivation and show you how to approach on the environment. And finally, I'll show you the derivation based on the assumption if the environment has certain losses. That's to say, when the environment's impedance model is assumed to have the spring and the damper together. Now let's move to the other camera and let's start our derivation. Okay, so this is force control lecture 2. Now let's recall what we had last time. We had the environment model assumed to be, that's of course environment's force model, don't forget, it's assumed to be the environment stiffness times x response minus x environment. This is nothing but the simple Hooke's law. That's the elongation on a spring times the spring constant gives you the force generated on the spring. Simply said, this is that equation. Now the next thing I would like to recall is the structure we have derived so far. If you remember, in our previous lecture we have derived that model where we had the continuously twice differentiable force reference, the scales of the control action alpha and beta both going to the reference and going to the response, the feedback channel, and our input being scaled by 1 over ke, which was giving us the desired acceleration, and that was the input of a plant with a disturbance observer. Now, in this structure, we can make certain modifications, and I'll try to address those modifications in the next slide, in the next derivation. So, let us try to draw the same scheme here. So remember the block diagram. We had something like this. So we had F double dot reference, F dot reference, and F reference. Those three items were being scaled by the coefficients alpha here and beta here, where F double dot reference was going as a direct input to our system. All with plus signs, of course. These are our references. Now, what we had in hand was simply this channel where we had, let me separate from the first side of the discussion, where we had the response position being scaled by beta ke and the response velocity being scaled by alpha ke. That is x res, response position, that's x dot res. And we were adding these items up and subtracting this from our reference to generate the feedback in the system. And overall, the equations told us that we have to scale everything by 1 over KE after all. So, if we play with this structure, of course, this was generating the x double dot desired acceleration that was going to the plant plus disturbance observer structure, right? And from which we were able to generate these feedback signals. We were extracting them from our plant. Now, I would like to take your attention to one point. This 1 over KE scaling can easily be embedded on those coefficients, which means that the block diagram given here in the first drawing can be modified as the one that I'm going to draw in the second drawing. Let us have a look at it. So we have here simply F double dot reference being scaled by, now 1 over KE will go out, 1 over KE. F dot ref, that's being scaled by alpha over KE, and F ref being scaled by beta over KE. What I did here is nothing but taking this KE out from this block and distributing over the components here and here. So we will add those three reference signals together. Okay. And then, as I will be distributing this KE before that summation channel, so it goes here as well, it should go to those two blocks. Let's take care of this part. We have here somewhere summation, and to our summation block I have beta times KE over KE, remember, which makes only beta as a scale, and here only alpha as another scale, following a similar way of thinking. So we will add these signals, and these signals will come here as a negative feedback, and of course you have here X response and X dot response. All together, this gives us the desired acceleration, which can easily be inserted on the plant with a disturbance observer structure. Well, that second drawing is nothing but the same, but it has nothing but the same functionality with the previous block diagram. Let me mark this as the second one. So these two block diagrams, the one in the top and the one in the bottom, have same functioning, but the reason why I decoupled this in the way that I showed in the second approach is twofold. First, you can easily distinguish and call this block as force feedback block. So that is the force feedback block from your system, and that is your reference, and this is the desired acceleration to carry out, to trace the given or the desired force reference. there is a specific goal why I moved to this structure. Now, here it's easy to make a modification and change the controller type to a proportional plus velocity feedback control style. Let me explain what I want to highlight in that graph. So, let me, by the way, mark the pages. This is the first page of the lecture 2. I'm sorry. This is the first page of lecture 2. Let me mark this as the second page. All right. So, what happens if we add a velocity feedback term? What I mean is modifying that equation, modifying that block diagram, I'm sorry, the second one, and adding here a new item that is CV times the velocity signal, velocity feedback signal generated from the plant, right? So here you have x dot response, the velocity response of your plant. What advantage would we have from this in comparison to the previous structure when we didn't have this? Of course, this should come with a negative feedback. Let me explain. In the original derivation, we have assumed that the contact with the environment was established. So, originally, contact with the environment existed. Now, if in the previous derivation there is contact with the environment, then you don't need this block at all. Your algorithm given here will function as a whole and carry out the force control for any continuously twice differentiable force reference of yours. But if the contact is not established, in other words, if your robot is here and the environment is here, but they're not contacting with one another at the beginning of the motion, then what would happen is that without the velocity feedback, your plant will try to enforce the force reference on the system and will move in a very fast manner to the environment and strike to the environment. That is an undesired situation. That's an unwanted situation in most of the robotic systems. So what we want is that your robot approaches to the environment slowly and contacts and then carries out the force control. So in order to handle this, that velocity feedback is necessary. When you add that, you simply change the dynamics of the closed loop control, and even though there is no response from the environment, there is no environment deflection, here with this velocity feedback, what you do is simply gently approaching to the environment and then touching, and after touching you have the response position and velocity from the environment. It's the deflection of the environment, and that gives you the opportunity to start force feedback, and all of this happens naturally in this block diagram. So we can add here to note that originally contact with the environment existed. If there is no contact at the beginning, and there is additional velocity feedback then the robot and effector will try to move with unlimited so what I mean is no feedback reference, which means that striking on the environment, and this is an unwanted situation in most of the motion control systems. So in order to avoid this, the way to avoid this is by adding external velocity feedback. So you can assume this, or you can comment on this in a different way. Have a look at this block. When there is no force feedback from your system, when this channel is closed, and you have 0 from here, you simply have certain reference from here and some feedback from that side. This is nothing but the simple velocity control approach we have been talking about so far, right? So you have some references, you have the feedback, you have the velocity feedback here, and the desired acceleration generated out of the velocity feedback. So your system goes with certain velocity. So this means that your system is bounded, and it goes with certain velocity until it reaches to the contact point with environment, and after the contact point the response velocity reduces dramatically, because as you approach to the environment and as you contact, your velocity reduces dramatically. So this channel will be then passive, and then this channel will be active. Your force feedback will be in action, and you will try to start carrying out the force control. So adding the velocity feedback has this advantage, has the advantage I've been showing here. I'm sorry. Well, this is kind of the end of the force control for environment without loss. Now it's time to have a look at force control applications for the environment with losses. So let me try to move to the other page. Page 3. Oh, there is again a problem with the camera. Let me deactivate and activate it again so that it may autofocus. Perfect. You can see it now. Well, the question is, what happens? If we have environment with losses. So what do I mean by the word environment with losses? Remember, in the previous application we had the F environment being represented as the stiffness of the environment times X response, the response position of your actuator, of your motor, of your robotic system, minus x environment. That's the total deflection generated in the environment. And this was model without loss. So this is actually pure spring model. Now, if we change this and if we get a little bit closer to what happens in reality, we have to modify the environment force as this one. Ke times x response minus x environment. So this is stiffness times the deflection in the environment plus environment damping times x dot response minus xe dot. Well, that is actually, let me write here, that's actually model with loss, or with another way of statement, we can call this spring damper model for the environment. Now, once again, this model is more realistic than this model, even though in most of the applications this model would be sufficient, would help us to carry out the force control. If you stick up with that model, both the derivation will be easier and the control performance will be improved in exchange of one detail, that here you have to also be able to measure the damping in the environment, which is not a very easy task. But you know, for most of the applications, for most of the cases, when you have an industrial plant, when you have standardized force control applications, it's not too difficult to come up with the KE and DE parameters of the substance to be processed under the robotic system. So once you make this analysis, once you know the stiffness and the damping of the environment where you are interacting with your robot, then it's not too difficult to carry out that motion control algorithm. Well, how to proceed? How to proceed? As usual, what we will be doing is to take our force and insert there a force reference, generate an error, and try to move that error to zero value in preferably in finite time, but in a very short time if possible, let me say. So assume one time differentiable continuous force reference FREF exists. Then formulate force tracking error. So let's have a look at it. The force tracking error EF will then be F reference minus F environment as usual, right? Now, if I take this equation and if I take that one and substitute here, what I would have would be simply EF is equal to F reference minus KE times X response minus X environment minus DE times X dot response minus X dot environment. Here I have to also make another remark, that this term will be equal to 0 for stationary environment. What I mean is that if your environment's contact position is stationary, it shouldn't have any derivative. Its derivative should be equal to 0. Then our force error can be recast as the force reference minus the spring constant times x response minus x environment minus the damping constant in the system, damping of the environment, times x dot response simply. Well, this is nothing, I mean that error is nothing but the same way of thinking with the previously formulated method. Here you have a natural velocity feedback in your system. Remember what we have done in the previous application. We have added the CV externally to take care of the situations when there was no contact with the environment. So when there was no contact, we had simple velocity control in the system, and once the contact is established, this will fade away and you will have the force control in the system. And that derivation here, what I mean is the environment model with certain loss would take care of the same mentality, would be behaving in the same way with the previous example. Now, just a second, guys. Okay, we are in the 4th page. Now, once we have the error, the remaining part is not too difficult. So, having formulated the error, the remaining part is simply an algorithm, so it is easy to enforce the error for zero value convergence. What I mean is, we will try to put our error in such a closed loop dynamics that it starts with any value and ends with zero value at the end. So if you look at this, what kind of approach we have to pick up depends on the structure. Now in the error, we have the response position of the system and response velocity of the system. And don't forget that while trying to enforce certain dynamics, we were trying to extract the response acceleration and give this to our plant as the desired acceleration, as what we have already done in simple velocity control, position control, or generalized error control applications. So take this error, since you have the derivative of the response, x response dot, only differentiation one time would be sufficient for that equation. So here is it. Claim EF dot plus KF times EF is equal to 0. Let me write would yield to the desired acceleration. How can we be sure of this? By simply substituting and carrying out the calculation. So, keeping that our errors here, and we will be substituting this error to this equation. By the way, I'll stop and start the camera again so that it may autofocus. Yes, that's what I wanted. So we will take this equation and substitute it here. Simply f reference dot minus ke x response dot minus x environment dot minus de x response double dot. So this is simply ef dot, right? Plus kf ef plus kf times f reference minus kf I'm sorry, ke, this is k not x, ke x response minus xe minus kf de x dot response should all be equal to 0 value. Now there are some terms here that will also fade away. There is only actually one term. Recall that we assumed stationary environment, which means that this should also go to 0 value. Well, I think I can use this pen. It's thinner than the previous one, and it's easier to fit that entire equation on the width of the page. With this pen, it's easier. I'll try to shuffle this equation. I'll try to take this equation and bring it to an easier format. So we simply have f dot reference, and from this point plus kf f reference, right? So these two faded away, and we have here, and here some terms that could be grouped. Let's start with the position term. Minus kf ke x response minus x environment. So this term is used. Now we can have a look at the velocity terms. Minus ke times x response dot here, and minus kf de times x response dot, right? So this term and this term is also used. Finally, we have here, let me kick this to the right hand side, should be equal to de times x double dot response. Well, it's not too difficult to derive the desired acceleration from that equation. Simply our response acceleration will be the desired acceleration, because we have the disturbance observer which can take any desired acceleration and result and output this actually as the response acceleration. Well, carrying out one more step of formulation here will give us this x double dot desired, which is nothing but x double dot response in a plant where we have the disturbance observer, should be equal to 1 over de times, we have the force terms, f dot ref plus kf f ref, I'm sorry, this is ref, okay, and then the feedback term minus here. Let's start with the velocity feedback, ke plus kf de times x dot response plus kf ke times x response minus x environment. So I think I can close this one, and the big parentheses. So, well, why did I use this much of space here? Let me try to rewrite it for you. X double dot desired is equal to 1 over dE times f dot reference plus kf f reference minus ke plus kf dE times x dot response, this is the velocity feedback, plus kf ke times x response minus x environment. So that is the position feedback in our system. Close the big parenthesis here and close the curly brackets. All right, this brings us to the point where we have the desired acceleration. Now the only remaining thing is to create the block diagram for the force control algorithm with for the environment with losses. Let's do it. So we are in the 5th page of our derivation. We will carry out a similar pattern and we will write here basically f dot reference and f reference. So f reference would be scaled by, let me bring the derivation here, so it will be easier to create the block diagram with the derivation for all of you. All right, f dot ref and f ref, I'm sorry, that reference. So f reference should be multiplied by kf and they're added up. So we have simply this plus and plus. This is our reference channel, right? And what we need is the velocity times certain coefficient, right? And position times certain coefficient. Well, here let me try to formulate it this way. This is with a plus sign, this is with a minus sign, and up to this point we have the C, let me call this CP and CV as two coefficients. First one is multiplying the position, right? So this is X response from X response minus X environment, I'm sorry, and this is X response derivative. So they should be summed up, right? Here basically CP will be standing for KFKE and CV will be standing for KE plus KFDE. So these are the control coefficients and I can take this from the summation point. Well, after all, that is this part plus this part, and don't forget to multiply everything with 1 over dE. This is the environment's damping, and that gives us x double dot desired, which should be given to a plant plus disturbance observer structure. And from this, don't forget that you can extract, let me put it here, you can extract the response position I'm sorry, response velocity directly here. For the response position, you have to make this plus and minus x environment, where x environment is just something constant. So what we do is from x response we subtract the environment's position, that's x response minus xe, multiply it with Cp and give it as a feedback, and use x dot response and multiply it with Cv and give it as a feedback. Of course, both of them are given as the negative feedback, don't forget. And on the left hand side you have the force references. So all together you generate the feedback loop, multiply with 1 over dE to create the desired acceleration for our system. Here the only note that we have to include at the end is this Cp is nothing but the term given here, and Cp will be this. Let me write them. Cp will be Kf times Ke, and Cv, the velocity coefficient, is nothing but Ke times, Ke plus Kf dE. These two are the controller coefficients or feedback gains. Well, with this information in hand, we put a full stop to the derivation of force control methods in the context of motion control systems. So what we did was we have covered the environment when there is a pure spring model, and we have covered the environment when there is spring damper model. So both of these models are valid, and in both of these models, of course, taking an additional velocity feedback on the pure spring model and using the spring damper model directly, you have natural behavior of the robot. So your robot approaches with velocity feedback to the environment, and when it contacts with environment, it moves to the force control mode directly with this algorithm. I will try to give certain block diagrams or try to make some simulations and put them as additional sources to the web in the following days. Thanks for watching.